Our next speaker will be Agus Sudjianto. He is Executive Vice President and Head of Corporate Model Risk at Wells Fargo and Company. And he is going to survey some of PiML's key features and I believe provide us a brief demonstration. Just for anyone who might be just joining us, I want to reiterate that this is a TechShares event put on by Open Teams, who gives you access to the best open source architects in the world to train, support, and deliver your software solutions. My name is Brian Skin. I'm your host. Again, the overall event is Quality AI and ML Models by Design with PiML. So Agus, thank you for sharing your experience with PiML with us. Take it away.
Thank you, Brian, and thank you, Patrick, for the very nice introduction. Let me start with this probably quick introduction of the motivation of PiML. And this is a tool that built with, as Patrick said, with years of experience in model risk management. And people that are in this panel today contribute significantly on the idea and shaping the direction what PiML today and what should be going forward as well. So through this forum today, we are hoping a lot more people will get engaged if we're looking at the tool useful to really shaping it in the future as well. So with that, Patrick talked about SR 11.7 about the adoption of ML today very rapidly, particularly in the financial industry. This framework that are built is not only applicable for financial industry but also applicable to other industry as well. But let me start with the problem with machine learning today, and I have a chart at the top. It's a chart. The horizontal is complexity of model. It's measured by the degree of freedom, more number of parameters basically. And the performance of the model, in this case, a predictive model for regression, so mean square error. So every dot in that line are a model, performance of a model with a certain hyperparameter. In this case, in this chart, this chart is from XGBoost, using XGBoost. So every circle there is an XGBoost model with different tree depth, different boosting step, different learning rate, different regularization. So that's what that chart is. So the more complex the model, will fit data very well. And then we split the data training to testing. We look at the testing, the more complex model, it also still work well too. So this is so many model in machine learning with different hyperparameter which result in different model. They perform almost similarly. So in overly parameterized model, a lot of parameter, like all in the machine learning, we encounter phenomena of model multiplicity. Many model perform almost the same way just based on the testing data. Or some people, the great Leo Breiman, the inventor of random forest, call it Rashomon effect, or something that people call it as well benign overfitting, meaning that from the testing data, we don't see it overfit. The model is it looks okay. The classic bias variance trade-off in statistical learning, where the more complex model will overfit, most of the time doesn't show up. So you can try yourself when you do a gradient boosting, you boost it a lot more. That means your model becoming more complex. The model get better and better until when you deploy it in production, then the environment change, the model will not work well. So a lot of problem in machine learning, then people have to retrain it very frequently because basically fitting noise, etc., etc. So the overly parameters model create many model that perform almost the same. So some model doesn't make sense. Some model makes sense. So model explainability is very important to uncover the potential trouble. So it can help to identify, to understand how sound the model is using model explainability. And when we talk about model explainability, most people, the field of XAI, explainable AI, typically talk about post hoc explainability, meaning the model is black box, then I'm going to apply post hoc explainer like LIME, SHAP, PDP, ALE, etc. To explain the model. The model is still black box. We apply explainability tool, but explainability tool can go wrong very, very easily. And the more complex the model, the more can be more wrong the explainability tool. So with that, the thinking is inherently, can we come up with inherently interpretable machine learning model? That's what we're thinking about. What's what in a lot in the PiML provide is basically providing machine learning models, sophisticated machine learning model, but inherently interpretable. So we're not risking ourselves with post hoc explainer that can go wrong. Then I talk about as well that we're going to talk about a little bit later is standard outcome testing. The practice today, we split the data, training and testing. We build model using the training data, then we evaluate it with testing data, and we feel good about it. Kaggle competition is like that too, right? So you win Kaggle competition based on the testing data. Then when you split it, basically you do random splitting. And that has a lot of flaws that what we're going to see a little bit later, particularly because when you test on that, we assume that the world stay the same, that the world is just like the training data. The distribution are IID between training and testing. And we know in real world, the world changed. And so anything that outside the training data or any data drift, the model will perform differently, it's not get detected. So that's what we're trying to address and motivate us to build all this end-to-end, how to build robust, reliable, and for responsible AI. So when we talk about this, how we solve this problem. So on the right-hand side, two key components that Patrick talked about in SR 11.7. One is called conceptual soundness. Conceptual soundness dealing with explainability, interpretability, as well as causality. And outcome analysis, we want to go beyond the standard test, simple standard testing split. So we're talking about weak spot. We're identifying which region in the model that the model is weak. We cannot just rely on AUC or F1 of overall model because the model failed in the weak area. So it's identifying the weak spot. Patrick gave an example of Uber accident. So identifying the weak spot where the model is weak. So the tool that's in PiML is designed for that. Reliability. Reliability is dealing with reliability of model output. Is uncertainty. How uncertain? We want to understand which region, with combination of data, with condition, that the prediction is less reliable. So that's part of it in the model diagnostic. And then model robustness is very, very important in this. If the noise, the data is corrupted, a lot of failure of machine learning in the medical field because of lack of robustness issue is when how robust any change, small change in the input, will it give how's the output going? How's the model going to react? Is this becoming completely different output with small perturbation? So a lot of research and adversarial attack and all of those are really dealing with that small changes, how the model will react. So lack of robustness is often a problem. In particular, I talk about benign overfitting, and when you, in the testing data looks good, but you deploy it become terrible. You have to refit it all the time because it's overfitting noise that's creating lack of robustness. Resiliency is, we know the world changes all the time, the environment change, the data drift. can we detect it? Can we test it up front before we deploy model? A lot of resiliency data drift are people are going through manage it through monitoring. Yes, model monitoring is important, but during model testing, we need to do that first so that we can anticipate what kind of drift, what factor of drift that really important that we need to monitor. And so when drift happen, we know exactly what we need to do. And then the other aspect is bias and fairness, that test that my next speaker will talk about in more detail. So this is what PiML cover all of this aspect. I'm going to go through very quickly and then just on some of this concept. So in PiML, when we talk about inherently interpretable model, it has several and many models in there that's available. We'll go through that a little bit quickly. And then all the testing and outcome analysis testing that I spoke about, those are available in PiML as well. When we use PiML, the workflow is we can PiML, you can use it in a low code mode, high code mode. Low code, you don't need the very minimum coding, or even almost no coding. I'll give you a demonstration on the low code later quickly. So in low code, it has interpretable machine learning model. From that, you can get exact interpretation. So it's no post hoc, exact interpretation. If you want to still apply post hoc, yes, you can apply post hoc with more confidence now to get a simpler explanation. You can do that. You can diagnose model in terms of robustness, reliability, weak spot, etc. And then you can compare various models and you choose based on the testing that you have and all of those things. Say, okay, here is the model you're going to use. So in real world, for high-risk application, we choose model not only based on performance, we choose model based on reliability, based on robustness, based on resiliency, based on bias and fairness. So all kind of consideration that we have to do. That's what the model compare is all about. If you want to get more flexibility, you can run it high code. It's a lot more coding, but you have a lot more flexibility, including if you want to do a black box model too, but black box model doesn't have interpretability, but you can still explain it using explainability tool, post hoc explainability tool, and compare. And of course, you can also in PiML, you can put, if you already have model, somebody already have built model, you can register pre-trained model and go through all the diagnostic tool in PiML as well. When we talk about interpretable model in PiML provide both the post hoc explainability tool at the bottom, but also the intrinsically interpretable model, particularly high performance model. It has ReLU-DNN, that you can make ReLU-DNN locally interpretable. And then if you need globally interpretable model, it has GamiNet, it has explainable boosting machine, or if you like to use XGBoost, it has XGB2, basically constrain the architecture to make the model inherently interpretable. I'm not going to go too much detail on this. I'm going to jump quickly into the some of the testing, and then we go to a quick demo, which Nick will go through a little bit detail. Feature selection in PiML, I would like to highlight a little bit. It has the correlation base. It has the traditional feature importance, but also it has causality base. If you need to choose features that are causal, in PiML, it has called independent conditional independent tests using Markov blanket, search for Markov blanket, variable that really impact directly the Y, directly the response, instead of variable that impact the other variable. And there are some benefit to have conditional independence model, because model typically more resilience when you have you choose your factor causal. In distribution failure test, Patrick talked about how to test for failure, identifying really region where the error is bigger. So that's slicing, understanding what variable in what variable region that the error is bigger. Region with large uncertainty. We talk about which region that has bigger prediction uncertainty, thus the model is less reliable. So reliability testing is in there. This is important. Both these two are important to identify model weakness so that model can be improved further. It has out of distribution testing, talking about model robustness. Basically, you in robustness, you perturb the input a little bit and how the performance changes quickly. And resilience is really drift. So we induce data drift, and then what variable are the most critical? If it's drifting, the most critical impacting performance, the performance will degrade the fastest. So this anticipate data drift. It has some simulation, it has some scenario of data drift, and then to anticipate, to understand how the model will change, the performance will degrade, as well as on the fairness as well, because you can build model that's fair, you can, but when the data drift, model becoming unfair too. So this is very important when we talk about resilience, performance, but also other attribute as well. With that, I am going to go quickly into a quick demo just to show how easy it is to. I'm not sure I understand. I'm sorry. To quickly go through this in a low code mode. So let me go to that. So here it is. I hope you can see the screen well. So the first one is basically importing PiML. After you install, you need to pip install from the GitHub and then construct the PiML experiment. So then you see, I'm going to demonstrate low code. So I'm going to run this. Select data. It has some demos data that you can use. In this example, I'm going to upload data from my machine. So I'm going to upload this data. So data get uploaded. You get the data summary. You can get the data summary. And in data summary, then you say, okay, this is a numerical attribute. This is categorical attribute. This is a credit example. This is the credit, the input attribute, and the objective is I am going to look at the status, whether the delinquent or non-delinquent. 1 is non-delinquent, 0 is 1 is default, 0 is 1 is non-default, 0 is non-default. We're going to use it for credit approval in this case. It has categorical attribute. In this case, it has race and gender as well. Race and gender, of course, cannot be used. So I'm going to exclude this. I'm going to exclude gender. I'm going to exclude race from my data. And then I can prepare for training. And then the preparation here, you have test ratio. I split it 80-20. Look, the PiML will read the output. You can specify the output, and this by default, the last column will be the output, and because of categorical, we'll do classification. You can do classification or regression, or you can put the sample weight as well. Okay, it has a simple EDA that I'm not going to go through, so I'm just going to show you how the low-code environment is just one line. You get all kind of things that you can get. Feature selection. I talk about you give the feature select. Is doing all the calculation of Pearson correlation, the simple Pearson correlation. Distance correlation is nonlinear, to identify nonlinear relationship using distance correlation. So you can see that as well. Feature important is a traditional feature important. In this case, using light GBM, feature important, but also has the conditional independent test. This is the causality test, which variable that are causal that you should use. So in this case, let me just, for a quick demo, I'll just use this. And confirm. And then you do train model. In train model, you have a lot of choice. This is the traditional statistical techniques. You have XGB2, how to make, this is basically XGBoost constrain XGBoost to make it inherently interpretable, basically XGBoost depth 2, so that you can get to up to two-order interaction. Caminet is the counterpart of that using neural networks. It's called Caminet. Or ReLU-DNN. ReLU-DNN is also inherently interpretable model. So let me do this. I don't have much time. I just want to demonstrate how easy to run. So this is running and you get the result. After you get result, you register the model for further analysis. And then you can do model explain. This is the post hoc explainability. So I'm going to just put it very quickly on this to illustrate. So there you have all the PDP and all of those, and then interpret. This is for inherently interpretable model. The explanation is exact. So this is the model explaining the model in very exact way. You have the main effect. You have the main effect exact, and you have the interaction. So under interpret for inherently interpretable model, you don't have the problem of post hoc explainability. And you can play around yourself and compare how trustworthy is sharp compared to the exact interpretability. It has global and local interpretability. So if it's in local, on the explain, under explain in the local, you will get all those lime and sharp. You'll get that. Okay. You can compare it with the exact interpretability. So for using model that is inherently interpretable, then you can see how trustworthy those post hoc explainability. It has model diagnose, looking at model resilience, one of them. Let me run this one very quickly. Then I'll turn it to my next speaker. You can see, I'm sorry. Let me pick quickly on this. Running model diagnostic. In model diagnostic, looking at accuracy, look at weak spot analysis. I spoke about weak spot analysis, looking at overfit, reliability, robustness, and resilience. I'm going to pick just resilience for now. So you can see how the model, the performance of the model in this accuracy, it can degrade very, very rapidly. The performance of model can degrade very, very rapidly. And what variable are important? In this case, mortgage is the most important. Shift it on the mortgage side, and let me pick the mortgage. Distribution shifted. The model will from the original one shift it to the low mortgage side. It will degrade very, very rapidly. Okay, so this one will give an idea upfront under different shift scenario how the model will degrade rapidly. And the shift scenario, there are several shift scenario that you can do what if analysis. So with that, I want to give. I don't have much time to deal with the other things like model fairness, but Nick is going to cover next on the model fairness. So with that, I'll turn it back to you, Brian.
Indeed. Thank you very much, Agus, for giving us this great survey of PiML. Really appreciate it.